Hi everyone, my name is Bruno Biat.
Hello everyone, I'm Irina Balcheva.
Today, Irina and I are presenting on behalf of the ggPMX team, composed of colleagues located in Europe, like Irina and I, and colleagues located in the US, like Matt and Sophie. ggPMX is an open source R package that we developed over the last few years with the aim at providing to the pharmacometrics community a model diagnostic toolbox that is efficient and versatile.
You may wonder, what is the value of another package in addition to all the R packages we use in our daily work? To answer this, have a look at this picture. This is us before the existence of ggPMX.
Indeed, no matter how comfortable you are with the use of R, you will need to write a lot of codes to generate diagnostic plots. You're going to spend more time than planned to debug your piece of code. And as Irina said, we might end up in the same situation as the lady on the screen, dealing with a lot of frustration, knowing that we have spent more time than planned in generating model diagnostic plots. The good news we have for you is that when you will start using ggPMX, it's going to save you tremendous amount of time in writing those line of codes, not only for you, but also for the people who will be asked to validate your work.
The beauty of ggPMX is that it is compatible with three of the most used nonlinear mixed effect model fitting software, namely NONMEM, Monolix, and nlmixr. Actually, it all started with the internal model building guidance that we developed. We realized that we have a gap in our workflow because each of us has his or her own code for diagnostic plots, and this created inefficiencies in terms of validation. We therefore designed the package having in mind its cross-software compatibility and consistency. A key feature of ggPMX is the automated generation of a diagnostics report. We allowed also for a lot of flexibility in terms of customization options. Finally, an important feature is the possibility to use it for submission work or publications. When we think of diagnostic plots, we all know that to assess the robustness of our model, we need to rely on a wide range of figures, such as NPD versus spread, NPD versus time, VPC, etc. Ultimately, you need to generate a long list of plots for each model coming with numerous lines of code. Here is an extract of the model building guidance from the section of modeling reports. This suggests where to place the different plots, either on the main body or the appendix of the modeling report. It should not be seen as a strict rule. We want to emphasize the content or the overall package of diagnostics that we consider essential for model evaluation rather than where they should go in the report.
Here on the slide, you have an illustration on the number of lines required when using ggPMX to generate a document containing all diagnostic plots we have mentioned on the previous slide. We call such comprehensive document a diagnostic report. After you have uploaded the ggPMX library using the standard library call, you'll be asked to perform two steps. The first one is to create a controller, an object containing all required information to generate the figure out of the outputs generated by one of the model fitting software. Depending on the software you are using, you'll be asked to use the corresponding controller creation function. The second step is to generate the diagnostic report out of the controller object by calling the PMX underscore report function. On the right-hand side, you have an illustration of the cover page of such report. Summary: by using ggPMX, you'll be asked to only type 2 lines of code to generate the diagnostic report. In the coming set of slides, we will be discussing the content of a diagnostic ggPMX report in detail. The report contains the comprehensive list of diagnostic plots we have discussed previously. All of them, starting first with the parameter table, capturing the parameter estimate value of your model, the corresponding relative standard error, and their shrinkage. In the core of the document, you will find the key diagnostic plots, such as NPD versus population prediction, NPD versus time, individual weighted residual versus individual prediction versus time, distribution of random effect, and DPC. In the next few pages, you will find additional diagnostic plots, ranging from the correlation of the random effect, the distribution of your random effect according to your covariates, standard diagnostic plots, such as observation versus population prediction versus individual prediction, residual plots, and individual fits. Over the last few pages, you will find again all the key diagnostic plots now split according to the covariates you have in your model.
A diagnostic report in ggPMX is nothing but a series of single plot comments. You have the possibility to access and generate yourself each individual plot without creating a report every time. We have given a few examples of various diagnostics here. You use the controller called CTR to call the single plot functions using the syntax PMX underscore plot underscore name of the graph that you want to display. For example, here you have DV versus spread, and this will produce the plot that you see on the right. These commands here, without additional arguments, will create plots with the default settings. Now, a little bit more details on how to create diagnostics reports. You have the choice of 3 report formats: Word, PDF, or HTML. Again, you create a report by using the controller and calling the function PMX underscore report. This function accepts at least 4 arguments: name, where you specify the name of the report, the save dir, which is the folder where you want to save it, and the extension. The 4th argument is specifying whether we create only a report, or in addition to the report, you may create a folder that contains all figures saved as separate files. For that, you need to call the option format equal both. When using this option, you get the folder ggPMX underscore gov that contains all figures saved as a separate file. The ggPMX gov folder is actually very useful when you need to refer to a specific individual figure in a submission document.
In addition of the nice reporting feature of ggPMX, there are several key features that comes with the package. In the next few slides, we're going to discuss some of them, such as graphical customization, multiple endpoints, BPC, and stratification. You will find the details of the remaining key features in the cheat sheet we will be presenting at the end.
The default settings are critical for the success of any package. We made sure that the default settings are good enough, but if you're not happy with them, You have the possibility to customize the figures yourself in a similar way as you would do with ggplot. On the left-hand side, you have the default call of the NPD versus time graph. And this is the default graph that you would get with this command. On the right, you have the graph where we changed a few graphical parameters. For example, we changed the color of the smooth line, we changed the type of point, we removed the draft label, and we changed the labels of the X and Y axis.
ggPMX has also the features to deal with multiple endpoints. The way ggPMX works is that ggPMX automatically generates one report per endpoint. It means that, for example, when you work with a PKPD model, you will need to create a controller according to the endpoint of interest, PK or PD endpoint. Here on the screen, you have an example of PD endpoint flagged as DVID equal 2 in your modeling dataset. Once you have created the controller according to the PD endpoint, you will be able to produce the report as you did before according to this specific controller. In our case, the diagnostic report will be focusing on the PD endpoint only.
Now, we would like to give you some information on the VPC functionality. To enable it, you need to provide a simulation dataset when you create the controller. You can use your preferred simulation software to create this dataset and save it in a file. The dataset should contain at least the 4 columns listed here. Once you have your simulation dataset, you need to use the sim argument of the controller function to create a PMX sim object that will allow displaying the VPC graph. The example here shows the syntax with a Monolix controller, but it's applicable in the same way for NONMEM and nlmixr controllers. Once you have enabled the VPC functionality via the controller, you can view the graph by using the PMX plot VPC function. Here is the default look of the VPC plot for a model fitted on a small dataset from a single study. To make the figure self-explanatory, we added by default a legend and a footnote. Both are adjusted automatically. Whenever you change some of the VPC settings, like the confidence level, the legend and footnote both adjust accordingly. The default VPC setting works fine for this simple example. However, in real-life situations, it will often be the case that you will need to adjust the binning. The next slide illustrates how to change the binning method. The binning is changed by using the bin argument and the PMX VPC bin function. Note that ggPMX uses the package class int to handle the binning. This package contains a few different binning methods listed here, some of them requiring additional parameters. You see in these two graphs the VPC of the simple model with two different binning styles. Bins are indicated by the rugs here. On the left, we used k-means with 5 bins. On the right graph, we used the style equal bins, as you see on the rugs, and there are 10 of them. Finally, we would like to give you a flavor of how graphs can be stratified. Our first example shows how to stratify the VPC. This feature, stratification, is particularly important for the VPC graph, especially when you're working with large datasets that pull data from different studies. In such cases, the only way to have a meaningful VPC is to stratify at least by study in order to have an appropriate binning for each design. In this example, we stratified the VPC by dose by using the strat_facet argument of the pmxplot VPC function. Additionally, we have specified that the scales of each facet can be different. Note that, as expected, statistics are calculated within each strata. Our final example is stratification of other diagnostic plots. Stratification is done using the arguments strat_facet for discrete strata, as we saw in the previous example of the VPC, or strat_color for continuous strata, applicable to all pmxplot functions. One or two-dimensional stratifications are possible. In this example, the NPD versus time plot is stratified according to study and sex. You get a result in the style of facet grid of ggplot. The smoothing is, of course, done within each strata.
Like in many R package that comes from RStudio, we put a lot of effort in creating 2 pages for the cheat sheet. We ask you to print out the cheat sheet whenever you'll be using the package and have the document next to you. All the key features are captured in a cheat sheet, and it will help you to navigate smoothly in using the package. In terms of documentation and resource, you will find the latest ggPMX version available on both GitHub and CRAN. All documentation and training materials, including this video, can be found on GitHub. With the package, you will have a comprehensive vignette providing all the details on how to use our package.
With that, we would like to thank you for your attention, and we're looking forward to interacting with you soon.
Thank you.